Hi everyone, I'm Brandon Haynes, and today I'll be speaking about VSS, a storage system designed to improve the performance of video data management systems. So as we all know, video is pervasive in our daily lives. Cameras surround us in ever-increasing quantities, and the amount of video being produced per person is increasing rapidly. Despite this, when you look at modern video data management systems, virtually all of them store video data as isolated, opaque, compressed video blobs. What do I mean by this? Well, in a relational data management system, users benefit from decades of fine-tuned optimizations that maximize performance both within the data management system and also at the storage layer. By contrast, video data management systems typically have none of these features. No internal support for ensuring video processing performance, and a bag of opaque blobs in a directory as an interface to video data. And so when designing applications, users have to deal with the consequences of these facts, where a common set of operators are often limited to simple reads and writes to and from these files. But this reality is highly suboptimal because video I/O and decompression is extremely expensive. And in many cases, these overheads constitute up to half of a video processing pipeline, leaving far fewer resources available for interesting work such as machine learning or computer vision. To see how these overheads add up, let's look at a couple of simple queries that one might see submitted to a video data management system. In the first query, let's assume a user has already ingested video data and run object detection to find regions containing automobiles. She then issues a query to retrieve frames containing red automobiles, perhaps in response to an Amber Alert. The video data management system might execute pseudocode that reads something like this. First, it iterates over each frame that contains a vehicle, decodes each such frame and runs a color detection algorithm. It finally assembles all the frames that match the color predicate and returns those frames to the user. Sometime later, let's assume that in our Amber Alert situation, license plate information has arrived about the vehicle in question. And so our user in response issues a second query. This query iterates over all previously detected red vehicle frames and returns the first one that contains the given license plate. And if we look at these queries, we can see some inefficiencies here. So in this case, we're actually decoding the frames containing red vehicles twice, once in the first query and here again in the second query. And these kind of overheads is what's causing video analytic pipelines to be so expensive. The intuition here is that we want to support the reuse of the intermediate result we generated in query 1, the decoded red video frames, from the first query and reuse them in the second query. And so to improve the performance of video data management systems, today I'll introduce VSS, a storage manager that optimizes these sorts of performance characteristics for video data management systems. And in particular, VSS optimizes video storage, fragment retrieval, and caching of video data. And it's designed to assist a larger, full-fledged data management system in improving end-to-end video query performance. And so the resulting architecture looks something like this. A video data management system subsumes VSS as its storage manager, leaving VSS to be responsible for the on-disk storage, retrieval, and low-level optimization of video data. And with VSS, if we return to the previous example, we can see that when a user submits the first query and decodes that red frame containing vehicles, VSS is going to cache that intermediate decode result. And then subsequently, when that second query arrives and requests the exact same video region, VSS can leverage its cache to produce the result without a need for that second expensive decode. But VSS in video caching is more than just naive intermediate result caching in the video context. So in particular, it addresses a number of challenges that are unique to this visual domain. So first, during query answering, it's important that VSS optimize both for performance and for quality of the result. So for example, if a data management system requests video data at 4K resolution, VSS can't simply select and return a heavily downsampled, low-quality variant. Let's also consider complex decoding dependencies between frames to ensure the performance is maximized. Second, cache video data has some unique characteristics that differentiate it from other domains. So for example, reads are more performant if we minimize the fragmentation of contiguous cached visual regions. And finally, while current systems deduplicate identical video, real-world video data is increasingly near identical and captured from physically proximate cameras, like in the case of autonomous vehicles or in traffic camera networks. And as we'll see, VSS can automatically identify these sorts of near duplicate video. So let's look in more detail at this first point and explore how VSS can optimize performance for reads and writes. So here we have an example where VSS has ingested a video and cached a number of fragments from previous reads. These fragments have different resolutions and formats such as H.264 or HEVC, and come in different resolutions ranging from 4K video all the way down to 1K video. And here we assume a new query has arrived requesting 1K video H.264 compressed between times 5 and 15, and I've illustrated that with this green box here. And as before, VSS can leverage its cache to produce an answer. And in this case, because the requested resolution is lower than everything else in the cache, VSS can leverage any cache entry to produce the result, and it does so. Like before, VSS will enter this new lower resolution fragment into its cache for subsequent use. But things are much messier in real-world cases, where cache video might overlap or have complex interdependencies. So for example, here we have that same read given a different cache situation. And in this case, VSS might utilize these entries highlighted in green to produce its result, or alternatively, it might choose these other regions highlighted in green to produce the result. And in most caching systems, we'd simply take whatever entry was the cheapest, convert it into the desired format, and return it to the caller. But video is a bit different in that there are complex, compression-related, frame-level interdependencies that prohibit generalized random access. And as such, in order to reformat those green regions, we might need to decode some, or in the worst case, all of the frames that either precede or succeed this region, that I've shown with white arrows. And this necessitates a more complex cost function with three different inputs. First, we need to consider the transcode cost to reformat a pixel from its cache representation into the desired output format. And then clearly we need to pay attention to the number of pixels that need to be reformatted. But finally and critically, there's this number of pixels inside frames that have these decode dependencies on the desired cached region. And while the cost function in the paper takes several other factors into account, we can envision a simplified cost function that looks more or less like what I've illustrated on this slide here. But unfortunately, this M term means that our choice of any particular fragment to use in answering a read operation depends on what other cache entries we've selected. Because if we've already paid to decode those dependent frames, we don't want to pay a second time in computing the lowest cost result. And as such, it actually turns out this problem is NP complete. And because of this, VSS employs a solver to find an optimal solution to which cache entries it should leverage in producing an answer. And see the paper for more details on this. But it turns out that paying attention to these interdependencies matters a whole lot. So here's a plot of VSS performance. On the x-axis, I show the total cache size after n random reads for a video we've ingested into VSS. And on the y-axis, I show the total read time to read back that originally ingested video. And I show VSS performance relative to a greedy baseline that doesn't pay attention to these low-level video compression interdependencies, along with this dashed white line that shows just reading the original video without any caching at all. And as we can see, VSS's knowledge of the low-level intricacies of video encoding leads to pretty substantially improved performance when reading video data. VSS also has low write overhead when ingesting video. So here I show a separate experiment where I write various datasets into VSS and measure ingest performance. And these include various real-world datasets such as Waymo and Robocar, along with synthetic datasets drawn from the Visual Road benchmark at resolutions ranging from 1K to 4K. And so here again I compare to and from writing to the local file system, and also to vStore, which is a recent video storage system out of Eurosys. Now here, VSS has modest overhead relative to reading and writing to and from the local file system, but is nonetheless competitive with these other systems in terms of write performance. So let's next look at how VSS manages its cache, again, given these unique characteristics of managing the storage of video data. Here's another hypothetical VSS cache configuration. Now let's assume for a moment that VSS has reached its internal storage caching limit and must evict one of these fragments. Which one should it choose? So first, some intuition about how VSS might make this decision. So if we think about it, we actually don't want to evict this region shown in orange, because doing so would increase the fragmentation of the cache, and this would result in a more complex problem space for subsequent reads, which we saw has complexity in the number of fragments. And this would put more stress on our solver, and so we actually might not want to evict this particular cache entry. And this is the first factor in VSS's eviction model, which considers fragmentation generated through eviction of a particular fragment. So specifically, it linearly negatively weights fragments occurring in the middle of a contiguous fragment, leading to us evicting fragments at the beginning of the end of a contiguous region more commonly than those in the middle. Second, we want to consider redundancy in terms of quality. And so here I've highlighted in green this 1K resolution video fragment. It's actually a downsampled version of a higher resolution 4K of the original video. Intuitively, we'd actually prefer evicting this fragment over others, since this higher resolution variant exists as a backup. And finally, VSS would never evict this red fragment, because doing so would mean that no other fragment contained visual data at the same original video quality. And so in this case, we would violate this rule for times approximately 18 to 20. So to summarize, VSS's eviction model takes three things into account when deciding which video fragments to evict. First, the amount of fragmentation created by a candidate. Second, the number of redundant, higher quality copies that exist. And finally, whether a baseline quality would be maintained post-eviction. Formally, VSS employs a weighted sum of these factors with some additional factors that I don't have time to discuss today. We discuss these and these additional complications and complexities fully formalized in the full paper. But here again, VSS's consideration of the unique low-level characteristics of video data really pay off in terms of performance. And so in this experiment, we write video data into VSS and again populate its cache with random reads. We then limit its cache to various sizes, as I show on the x-axis, forcing different amounts of eviction inside VSS. And then finally, we read the new video and observe how well VSS is able to utilize its remaining cache, and we show that performance in terms of seconds on the vertical axis. We show runtime for both VSS, along with vanilla, least recently used LRU eviction policy. And here we can see that the details matter. VSS is able to offer improved performance relative to LRU by paying attention to those low-level video details. And so finally, I'd like to briefly discuss VSS's approach to deduplication of identical and near-identical video. To illustrate this, imagine that we have two videos ingested inside VSS. And note, in this case, these are not two cache representations of the same video, but are actually two independent videos written as separate entries inside VSS. So for example, imagine two YouTube videos had been uploaded into VSS by completely different users. But in many cases, pairs of videos may contain identical or near identical representations of the same visual data. This comes in two flavors: identical video data and near duplicate video data. And so in the identical video case, existing systems can fingerprint and detect this sort of duplication, as does VSS. But in the second, increasingly common case is this near identical video, which differ only by perspective. And so the example I show here is drawn from the robot car data set, where two adjacent cameras have been mounted on a vehicle, and they capture almost but not quite the exact same perspective. And we see examples of this in autonomous driving and in traffic camera networks. And here existing systems are unable to reason about this near identical form of video data. But VSS is able to identify and, as we'll see, deduplicate the overlapping regions. Further, it actually performs this process transparently and future reads operate as if the deduplication optimization had not been applied. The calling video data management system is not even aware that this optimization has been deployed. So at a high level, the process works like this. Consider two cameras, C1 and C2, that are physically adjacent and capture an overlapping field of view. Now I show two representative frames from these cameras as frames F1 and F2. If we look closely at these frames, we can see that they have a region that overlaps. These regions I've labeled O1 and O2 contain near identical data from slightly different perspectives. Now, importantly, we can't just simply isomorphically merge the two regions. So for example, if we look very closely, we can see that the crosswalks in each video are at slightly different angles. Instead, VSS establishes a homography between the overlap candidates O1 and O2 and uses this homography to project one overlap region into the other overlap region. And so here we show this transformation applied to O2, which I've now relabeled O2 prime. VSS then merges these two images and encodes this combined overlap region separately on disk. But these overlapping pixels are then only stored once instead of separately. Note also in the paper we describe additional methods of merging the two videos beyond just overlaying O1 onto O2. And so that gives you a high-level sense of how overlap is deduplicated between a pair of videos. But how do we identify the overlap candidates in the first place? VSS employs the following process to do so. So first, whenever a fragment is decoded through a read or a write, as a byproduct of that read, we generate a color histogram of an exemplar frame drawn from that fragment. We then cluster these histograms and consider candidates that have low cluster distance and density. And for each potential candidate we draw from the cluster, we extract key point features. And when the number of those non-ambiguous key points between a pair of exemplar frames meets some threshold, we then consider it a likely candidate for joint compression. And so we give it a try, right? And we do so by generating a homography between the exemplars and doing the projection process that I showed in the previous frame. If the homography indicates that there's a good amount of overlap, we'll apply the joint compression process. If homography indicates that the video data are identical, we skip to a deduplication process as if the video data were identical. Now, critically, if for any of these steps we happen to detect that the quality would be degraded beyond some user-specified limit, we abort joint compression entirely and mark the candidate pairs as being incompatible for future consideration. And as you might expect, writing this redundant overlapping region only once instead of twice greatly reduces the storage required to store a pair of near duplicate videos. And so in this experiment, we vary the amount of overlap between the videos and record the amount of storage size we saved as a percentage by applying the joint compression optimization. And so in this case, we get about a third reduction in total file size when applying this optimization, and performance tends to peak between about 30 and 45 degrees of overlap, which is common in areas like autonomous vehicles and traffic camera networks. Note that as the overlap increases, we tend to see a fall off in this performance benefit, and this is because as our region of overlap increases, the non-overlapping fragments get very narrow, and video codecs tend to have much higher overhead in these cases. Okay, and so with that, I'll conclude. Today I introduce VSS, a storage manager designed to support video data management systems. VSS handles the low-level storage, retrieval, and caching details associated with managing video data. By paying careful attention to these low-level storage details associated with video storage and compression, it's able to deploy a number of optimizations that improve performance and decrease storage costs. These include a solver-based query answering system that jointly optimizes read time and quality, all the while paying attention to the complex interdependencies between frames. It comes with a video-aware eviction process that minimizes fragmentations and ensures that quality is maintained for future reads. And finally, it comes with deduplication optimizations for identical and near-identical video data. We describe these details along with a number of other optimizations in our full paper, which I invite you to check out if you're interested in further details. And so with that, I'll close. Thanks so much for listening.